So the purpose of this lesson is going to be to review all of the different types of reactions that we reviewed over this summer in review of first year chemistry, and then to add on a little bit in order to prepare for your lab. So the first type of reaction that we looked at were synthesis reactions. And in a synthesis reactions, there are three different main types that we looked at. The first one was the formation of a binary compound, meaning you take two elements, combine them together to form one product. The next type is a metal oxide in water. So you take a metal that's bound to oxygen in an ionic bond, add water to it, and you'll form a base. Remember, a base is a metal that is bound to hydroxide. And the last type is a nonmetal oxide in water. And so you have a nonmetal and oxygen reacts with water, and it's going to form an acid. Remember, an acid starts with hydrogen, H, then it has a nonmetal, and then it has oxygen afterwards if it does have oxygen. Some do not. So as practice, I'm given a piece of sodium and it's placed in hydrogen gas. So I start off with sodium, Na, and it's going to react with hydrogen gas. Remember, hydrogen is diatomic, so it's H2, and that's going to produce sodium hydride because this is the first type of reaction, the formation of a binary compound. Now I do need to balance, so since I have two hydrogens on the left-hand side, I need to put a 2 in front of sodium hydride and then a 2 in front of sodium. The next type of reaction is a decomposition reaction, and there are 6 main types of decomposition reactions that we looked at. Look those over and refresh your memory on those. Okay. Notice that a lot of the decomposition reactions are simply the reverse of synthesis reactions that we looked at. And so let's look at an example. I start off with calcium hydroxide and I'm told that it decomposes. Well, calcium hydroxide is CaOH2. And that's going to decompose. Now that's a base, and so that's going to decompose into a metal oxide in water. So the metal here is calcium and then oxygen. So you've got CaO because their charges cancel each other out. And then the other product is water. And if I check, I'm actually already balanced. So that's one example of a decomposition reaction. The next type of reaction we're going to talk about are double replacement reactions. Now in a double replacement reaction, you have two different compounds and they're going to just switch partners. I called it innies and outies. The elements on the outside are going to join together and the elements on the inside are going to join together. And the other component of this was net ionic reactions, which we're going to look at once more. So if you look at this example here, I start off with copper chloride and sodium sulfite. So copper chloride, copper has a 2 charge, chlorine has a -1 charge, so that would be CuCl2. And that's added to sodium sulfide. Now sodium's +1, sulfide's -2, so that's Na2S. And so my outies, which are copper and sulfur, are going to combine together, and sodium and chloride are going to combine together. So I end up with NaCl, and, well, copper is +2, sulfide is -2, and so I end up with just CuS. Now I do need to balance, so I'm going to have to put a 2 in front of NaCl to balance that, and then everything else is already balanced. Notice that was the molecular equation. I didn't take into account any of the solubility rules, which I need to do right now. So to write the complete ionic equation, what I do is anything that's soluble, I need to break apart into its ions. So if I look at my solubility table, copper chloride, chlorides tend to be soluble, and copper chloride is. So copper is going to break apart into its ions. It's going to be copper with a 2+ charge. And I'm going to add that to, well, I have 2 chloride ions, so 2 Cl minuses. And I'm going to add that, well, sodium sulfide, also anything that sodium's bound to is going to be soluble. So I'm going to have 2 sodium ions and then a sulfide ion. And that's going to produce, well, sodium chloride is going to be soluble. So I have 2 sodium ions and 2 chloride ions. And then if I look for the rule for sulfides, copper sulfide is actually insoluble, which means I leave it alone. So to write my net ionic equation, what I need to do is I need to get rid of any spectator ions. And spectator ions are simply ions that are not directly involved in the reaction, meaning they do not change at all. So if you look, the 2 ions that are not involved are going to be chloride and sodium because they remain the same on both sides. And so once I eliminate those spectator ions, my net ionic equation is whatever is left. So I've got copper ions, I've got sulfide ions, and that produces copper 2 sulfide. And that's my answer. Now, the other type of double replacement reaction that we're going to talk about and we're going to use extensively at the end of this class are acid-base neutralization reactions. In order to write the net ionic equation for these guys, though, I need to identify strong acids and strong bases. Strong acids and strong bases are going to be strong electrolytes, meaning that they dissociate completely in solution. So I'm going to break them apart into their ions. If they are weak bases or weak acids, they do not dissociate completely in solution, so I leave them as the compound. So my strong acids, these are two lists you're just going to have to memorize. My strong acids include hydroiodic acid, hydrobromic acid, perchloric acid, hydrochloric acid, chloric acid, sulfuric acid, and nitric acid. So there's 7 of them there. The strong bases are a little bit easier to remember. It's all of the group 1 hydroxides, and then calcium hydroxide, barium hydroxide, and strontium hydroxide. So all of these, all 13 of these, are going to dissociate completely in solution. If you have an acid or a base that is not one of these, it is not going to break apart, and it's going to remain as a compound. So if you look at this example, I give you perchloric acid and calcium hydroxide. Well, the formula for perchloric acid is HClO4, and that is a strong acid, keep in mind. And that reacts with calcium hydroxide, so CaOH2, which, by the way, is a strong base. In an acid neutralization reaction, notice I included this on the same slide as double replacement reactions simply because they are double replacement reactions. So my outies and innies are going to go together. Notice my outies here are a hydrogen ion and a hydroxide ion, which would produce water. And then calcium and perchlorate are going to combine together. Notice calcium has a +2 charge, perchlorate has a -1 charge, so it'd be CaClO4 2. Now, I need to balance, so I put a 2 in front of perchloric acid and a 2 in front of water, and now I'm balanced. The next part is to break apart anything that is soluble or any of my strong acids or bases. So since perchloric acid is strong, I need to break it up into its ions. So I have 2 hydrogen ions and 2 perchlorate ions. And then I also have, because calcium hydroxide is a strong base, a calcium ion and 2 hydroxide ions. And so that's going to produce 2 waters. Water doesn't break apart. And then calcium perchlorate is actually soluble, so it's going to break apart into its ions. So I have calcium with a 2+ charge, and then I have perchlorate, which would be 2 of them. And now to write the net ionic equation, remember you simply eliminate your spectator ions. So I'm going to get rid of my perchlorate ions, and I'm also going to get rid of my calcium ions. So what I'm left with is 2 hydrogen ions reacting with 2 hydroxides to produce water. So that is a neutralization reaction because you took an acid and a base and made a neutral solution, meaning you made water. In any reaction, you will see a change in heat. Now, a reaction can either gain heat or it can lose heat. So if you look at the diagram on the left-hand side, the reactants have greater energy than the products, meaning that energy was lost. Therefore, this is going to be an exothermic reaction. Notice the activation energy, which is the energy required in order for a reaction to occur, that is represented by the distance between the energy of the reactants and the peak, the highest part of that energy profile. Now, if I wanted to figure out the reverse activation energy, I would start at the products and go all the way up to that peak right there, which happens to be the sum of the energy released and the activation energy. So that's an exothermic reaction, energy is released. If you have an endothermic reaction, then the energy of the products is going to be greater than that of the reactants because energy is absorbed. And by looking at the difference between the energy of the products and the reactants, you can figure out how much exactly is absorbed. And then you can also determine the activation energy. So notice for this particular endothermic reaction, it has a higher activation energy than the exothermic reaction that's being shown. So we looked at potential energy diagrams 2 slides ago, and I'm going to review this with an example. The first thing I need to talk about, just as a review, is the activation energy. Now, the rate of a reaction depends on the activation energy. And so if you have a really low activation energy, that means that the reaction is going to be faster simply because it's easier for those reactants to acquire the necessary energy in order for that reaction to occur. If you have a very high activation energy, that also means that the reaction is going to be slower because it requires so much more energy. It's going to take more time. And so if you look here, it's giving you 5 different graphs, and it asks which describes the pathway of a reaction that is endothermic, meaning it's absorbing energy, and has high activation energy. And so if you look here, B is exothermic, E is exothermic, C, we've never seen something that looks like that before, so A and D are really your only options. Now, it's hard to tell if D is actually endothermic, meaning that the product's energy is higher than the reactant's energy, but let's say it is. The next part is it says that it has a high activation energy. Well, the only one there that shows a high activation energy and is endothermic would be A. So let's talk about the rate of a reaction and what is actually required for a reaction to occur. And so the collision model tells us that in order for a reaction to occur, molecules must collide. And specifically, the higher the reactant concentration, so the more reactants there are, and the higher the temperature, the greater the reaction rate will be. And this is because if you have a higher concentration of reactants, that means that they're going to collide more frequently. And if you have a higher temperature, that means that the reactants are going to collide with a greater amount of force, ensuring that the rate at which the reaction occurs will be greatest, because you want the most frequent collisions as possible, and you want also the collisions with the greatest amount of energy. That will ensure that a reaction will actually occur. So in addition to this, in order for an effective collision to occur, the first one is that there must be sufficient energy, meaning that the activation energy has to be overcome. The second is that not only must the reactants have sufficient energy, they must also have the correct orientation. So they can't just hit each other in any orientation that they want. There's a specific orientation that they must collide with one another in order for that reaction to occur.